Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we were talking about fluid mechanics. In that case we discussed about Bernoulli's principle and their applications. Some of the applications like Magnus effect, Venturi meter, speed of efflux and all that we discussed. Let's continue here with some application of like Bernoulli's principle. So these things will give you more idea how exactly we apply Bernoulli's principle in case of problems. So let's start with one simple case. So velocity of liquid coming out of small hole of large vessel containing, so it's given clearly large vessel means we will definitely consider, let's say this is area as A, this is A naught, then we can take definitely A is very greater than A naught. Okay. Containing two different liquids of density 2 rho and rho. Only the different thing here we are encountering is that here two liquids are mixed. Two liquids are filled in the vessel, and this is density 2 rho and this is density rho. So how we deal in this case? There is simple one method. You just need to learn that, is it? So we can apply basically Bernoulli's principle between these 2 points. Then we need to take care of this, is it? Density is different, so either way you can go. One way you can directly go between these 2 points, is it? Let me mark, this is point 1, this is point 2 and this is point 3. So we can go it in two way by applying directly Bernoulli's principle between point 1 and 3 and between point 2 and 3. In either way, this just different way, different methods of different calculation part. Learn both the ways. Let me tell you. So apply Bernoulli's principle or Bernoulli's theorem between points, let's say 1 and 3. Let me apply directly. Okay, so again for 3 I will take the reference line from here itself. So point 1 I can write, let's say P1 plus half rho V1 square plus rho GH. Here we need to write these things properly actually, because so let me write it for point 1. So point 1 pressure I can write P naught. Velocity, because this is large tank, so we can take the velocity of this free surface will be almost 0. So I can write the kinetic energy is equal to 0 plus next we need rho GH. Now which rho we will consider? This rho, this rho. So we need to consider actually both and their cumulative effect, like 2 rho GH this and rho G into 2H this. So it will be, because I am taking reference here, just remember it, I am taking reference here, then I need to go from here. So whatever that it's coming, like I went from here to there, it's 2 rho into G into H, and then from here to there it's rho G into 2H. So it will be 2 rho G into H plus this is rho G into 2H. I hope you are clear. This is point 1. Then at point 3 I can write P naught plus half. Now the liquid coming out from here is having density 2 rho, so we will write half 2 rho into V square, right, plus 2 rho G into H is equal to 0. I hope you are understanding, you are clear with this term. P naught we can directly cancel. Here this is 2 rho G, 2 rho G, it's 4 G rho into H. Here we are left 2 this is cancel, this is 0 simply, so this is rho V square, and rho also gets cancelled, and this implies V is coming out to be 2 under root GH. So this is the way we can solve it, we can get the answer. Another way is, because if I am, let's say what I need ultimately pressure. If I am getting the pressure at this point, then I can apply Bernoulli's principle between point 2 and 3. So you know the pressure at this point is P naught. Then pressure at this point will be equal to how much? P will be equal to P naught plus rho G into 2H. And then I can apply Bernoulli's principle between point 2 and 3. So let me get the answer of same velocity by applying Bernoulli's principle between point 2 and 3. So Bernoulli's principle between point 2 and 3. Okay, so in this situation the pressure at point 2 will be equal to this. I can write P2, is it? Again, because this area of P2 is again equal to the area of vessel, so velocity of point 2 I will take that 0. The free surface, this surface is again falling with almost 0 velocity. It will be like negligible velocity, like very small velocity, but we take that almost equal to 0. So then I can write P2 plus half into 2 rho, this is, you can write 2 rho into V square plus, is it rho G into, or let me substitute directly the values, then it will be like P2 is P naught plus rho G into 2H plus kinetic energy, I will write it 0, and for P3 point it's again P naught plus half, now 2 rho into V square, is it, and this is the pressure, plus with reference because, just listen, this complete quantity is the pressure. Next I need kinetic and potential, so kinetic will be 0, potential I need to write, potential will be equal to 2 rho G into H, 2 rho G into H, that will be equal to P naught at point 3 half into 2 rho into V square plus potential 0. So now here also again P naught getting cancelled, this is 2 rho GH, 2 rho GH, 4 rho GH, this gets cancelled, 2 gets cancelled, rho V square, 4 rho GH, rho gets cancelled, and we are getting, again simplifying, we are getting 2 under root GH. So we can see exactly it's like same method, you can directly go between these 2 points, or either if you are finding it difficult, you can go from here to there, you can easily express the pressure. Now point 2 and 3 you can take, both will be in same liquid, then you don't have to worry about the density, whatever the density wherever it is coming, just simply substitute the density equal to this, like 2 rho, simplify it, you will get straightforward answer. So this is just, you are learning it, you are seeing it first time, then you might have like little bit of issues, but just remember the approach, learn the approach, how we are dealing, how we are doing it, and carry forward, like apply it wherever you are requiring. Let's see one more application based on it. So equal volume of 2 immiscible liquids of density rho and 2 rho are filled in a vessel as shown. So here also we have one vessel and 2 liquids density rho and 2 rho, height, equal volume are filled, and 2 small holes are punched at depth of h by 2. So from here this is at depth of h by 2, and another hole is punched here, that is at a depth of, this is at 3h by 2. Okay, and here this liquid is in liquid hole is in a liquid of density 2 rho. From the surface of the lighter surface, okay, if v1 and v2 are velocities of efflux, so let's say here velocity is v1 and here velocity is v2, then you are asked to find v1 and v2. So it's almost similar problem, just a little bit different. Let me solve it. So first thing is, just look at v1. v1 is equal to what? We know actually already, velocity of efflux, simple, one liquid density rho, and height from the top surface of this hole is what? H by 2. So v1 I can straightforward write directly by using the formula of velocity of efflux. It comes under root 2gh, and substituting the value h is equal to actually h by 2 here, is it? So this comes out to be v1 is equal to under root 2g into h by 2. Let me write it some capital H. This comes out to be under root gh. This is v1. Now next, for applying finding the velocity v2, I need to apply Bernoulli's principle between. So again I can go exactly in this manner, 1, this is 2, and this point you can take 3. So you can write the pressure of point 2 will be P naught plus rho GH. Then you can apply Bernoulli's principle between point 2 and 3. So let's apply Bernoulli's principle between point 2 and 3, right? So that will be equal to what? Again, pressure of point 2 is P naught plus rho GH. I hope you are understanding. Plus point 2 with reference to point 3, so it will be, height will be h by 2. So I will write 2 rho into g into h by 2. Kinetic for point 2 I will take that 0. This is equal to pressure of point 3 P naught plus rho GH 0 plus half rho V square, and rho here I will be taking 2 rho. 2 rho into V square. Now P naught gets cancelled. This H, I am like 2 gets cancelled. So rho GH, we are left here with 2 rho GH. On this side only 2 gets cancelled. So it's basically rho V square. So this comes out to be 2 rho GH is equal to rho V square. Rho gets cancelled. This implies V, I am getting under root 2GH. So this is actually your V2. Then the ratio of V1 by V2 I can write easily. So here V1 by V2, that under root GH divided by under root 2GH, that is coming out to be 1 by under root 2. This would be the answer to the problem V1 by V2, 1 by root 2. So this is your problem. We can just check the calculation part. V1 we are getting straightforward. Rho GH is H by 2GH. Yes. So it gets cancelled, and then for point 2 and this V2 velocity, we applied P2 pressure, P0 plus rho GH. That's correct. 2 rho into G into height. From this reference, I can take height H by 2. That's correct. P0 plus half 2 rho into V square. That's simplifying. So this is becoming 2 rho, and this 2 rho gets cancelled. So yes, we are simplifying it and we are getting the answer. So that V1 by V2 is coming out to be 1 by root 2. Okay, let's talk about next a small topic that is called siphon. Siphon, it's like a tube basically, and it work without power, without supply of energy, and it's like just imagine here, let's say liquid is filled in this tank and one tube is passing over it, and I'm asking you just connected it and then no liquid will flow. Actually you try, no liquid will come out of this tube. But once you I think everyone might have even experienced it, might have even tried it at their home. So let's say some tank is there, some water or something, liquid is filled in that tank. Then you take one tube, one pipe, and dip one end of that tube in that liquid and then suck with the other end, sometime with your mouth or maybe something else. And once liquid once start flowing, then you leave it, automatically it keep on flowing. So the question is, what causes this liquid to rises actually? Because falling here we understood, but what is causing this liquid to rise even at higher level and then going down, is it? So this tube is basically called siphon. So siphon, it's we can define it as a tube or pipe through which liquid from higher level can be withdrawn from higher level to lower level. A liquid can be moved from higher level to lower level by how? So once this actually we will understand it, the physics behind it, how it exactly works. The reason is that it moved by atmospheric pressure forcing it up the sorter leg. So what happened actually, once it started, once you suck here and then leave it, then pressure here drop. So this lower pressure pull this liquid up in this tube, and then weight of this liquid in this larger leg, is it, or bigger leg, weight of this liquid forces it continuously downward. So that is what exactly it work here. So we can define it, it is a tube or pipe through which liquid can be moved from higher level to lower level, is it, higher level to lower level by atmosphere pressure forcing it up the shorter leg. So this is shorter leg, one is longer leg. So atmosphere pressure is forcing it up the shorter leg, and then weight of this liquid in the longer leg, is it, while the weight of liquid in the longer leg causes continuous downward flow. This is termed as siphon. Here we need to understand what exactly what is the pressure here and how the velocity, what will be the velocity here, on what factor exactly it will be depending, is it. So let me define here, and I am taking this velocity is this height as let's say h2, this height as I am taking h1, and let's say this is my point A. Here you can take point just down here, I am taking B, this is C, and this is D, E, and let's say here it's F. Okay, so then we can use Bernoulli's principle. So let's say here speed is of the fluid flow is V, then by continuity equation we can say if area of cross section of the tube is constant, then the speed of fluid flow at every point of the tube will be constant, is it. So here let's say let the speed of fluid coming out, liquid coming out from the tube is V. We will calculate exactly on what factor, and let's say the density of the liquid is rho, and this height I am taking h1, this height I am taking h2. Then we can get first like pressure at this point. So pressure at a point will be equal to what? PA. I can write PA is equal to simply P naught, atmosphere pressure at point F, PF will be also equal to P naught, right? Let me apply Bernoulli's principle between point A and F. Let apply Bernoulli's principle between point A and F. So what it implies here, I can write PA P naught plus velocity of at point A, I can take it almost equal to 0 plus from here reference height I can take its rho g h2. Pressure at point F will be like P naught plus half rho V square plus it will be equal to rho g h is equal to 0. Clear? P naught gets cancelled out. Here this is simply 0, rho getting cancelled out, and we are getting V is equal to under root 2gh2. So first thing is, the velocity of fluid coming out from here is depending on this height, where you are holding this tube, and from this lower end of tube, what is the level of liquid in the tank. On this height, your velocity will depend. So velocity or speed of liquid depends on the height of liquid level in the tank from open end of larger leg of tube. So that is what exactly, like it depends on open end of larger tube. Next, like sometime you are asked to find pressure at point D. So again, like what I can write, VF will be equal to VD by continuity equation, and this can be written as under root 2gh2, right, by continuity. And then I can apply here, if I am writing the pressure at point A and D, then A you can write VA will be almost equal to VC, that will be equal to 0 actually, and pressure will be equal to P naught. So let me apply Bernoulli's principle between point A and D. That will be, I can write PA again P naught plus half rho into 0 square plus from this reference I can write it's equal to 0. Next, PD plus half rho V2 square plus rho GH 1. Is it? P naught getting cancelled, this is complete 0, and no, it's not getting cancelled, it's PD, it's P naught. So this implies we can write, we can substitute this value also, V2. So P naught minus rho G H1 and half rho V square, so half rho into V2 is 2G H2 is equal to PD. 2 gets cancelled, and this implies PD is coming out to be P naught minus rho G, that is H1 plus H2. So you can see actually here pressure at point D is becoming very low, and this low pressure is pushing this liquid up in this salter leg. Later on, this weight of liquid is pulling it continuously downward. That help in supplying, in moving the liquid from tank at higher level to lower level with the help of this tube, and this is called as your siphon. So overall this setup is termed as siphon. So speed of the siphon, speed of the flow at this point, you can get it directly. If the area of cross section at this and this will be different, then you need to use the continuity equation for getting the velocity at point T. Here I am assuming area of cross section of the tube at like a complete tube is constant, so that's why speed of fluid here will be equal to speed of fluid there, right? And speed, because this is submerged, dipped in basically liquid, so C and A will be taken as same, that is 0. And rest thing is this simple application of Bernoulli's principle. So now you must be clear that why and what exactly causes the fluid to come out from the tank. Is it by even going at higher height to finally coming out down? Is it? So simple thing, the low pressure here pulls the liquid up, and then weight of this liquid in this tube is pulling it continuously downward, and that causes the liquid to move from higher level to lower level without any pump, without any external work. Initially you need to start it. Once you start it, then it will continuously keep on moving, because to carry on to like continuously, here the pressure must be reduced, and that will happen only once the process start. So that initially you need to start, once then done, it will keep on continuously going. So sometimes some problems, small things are asked to you. If you are understanding this concept, this theory, you will be in position to answer those questions based on this concept, that is called siphon. Okay, let's see a few more cases. So here we have one problem. Let me read it first. A candle of diameter small d is floating in a cylindrical container of diameter. This is the candle, diameter small d, floating in a cylindrical container of diameter capital D, and capital D is very, very greater than small d as shown in the figure. It is burning at the rate of 2 cm per hour, then top of the candle will. So the candle is burning means in 1 hour the candle length will burn by this is 2 cm per hour. Then what will happen to the top of the candle? So different options, it will remain at the same height, means if it is burning, so this will shift up by 2 cm and the top of the candle will remain same height according to option 1. We don't know whether it's true or like false. Fall at the rate of 1 cm. So candle is burning at the rate of 2 cm per hour, but option 2 is saying it's falling at the rate of 1 cm per hour. Fall at the rate of 2 cm per hour and go up at the rate of 1 cm per hour. So these are different options. Let's talk about it now. So first thing is, what is happening here? Is it, let's suppose if it is not burning, then what is happening? It's exactly half of the length is outside, half of the length is inside. Means this much length, the buoyancy force acting on this much of volume of liquid displaced by this much length of the candle is sufficient to balance its weight. So you can say the density of a candle will be half exactly, right? So means we can understand that if L is the length of the candle at any moment of time, then L by 2 must be submerged in the liquid to balance its weight so that it's not sinking. Clear? Or because it cannot be like even less than this, it cannot be even greater than this, because it's in equilibrium. So what it mean now? See, if the candle length is decreasing by 2 cm in 1 hour, this length outside will be what? L minus 2 cm. But here it cannot be L, because in that case the weight outside it will be low, and the total weight will be low, but more volume will be submerged, because earlier the total weight was balanced by this L length. So now here L by 2 is the length left, so it must be like what exactly? We can say the inside length must be also equal. So it is decreases by 2, so then this also decrease by 1, so that both side it's balanced. So if it is like rising by 1 cm, then it will be like outside it is L minus 1 length, and inside also it will rises by 1 cm. So inside length will also become L minus 1 cm. Now you can see exactly the level, is it outside length L minus 1 cm, inside length L minus 1 cm. So they will balance each other. So that means what is happening? Effectively the candle was 1 hour ago, it was, the top was here. Now after 1 hour it has fallen by 1 cm. So the answer to the problem will be fall at the rate of 1 cm per hour. I hope you are understanding. This is all logical. You can even calculate it exactly like by just balancing its weight. can be shown mathematically also. So let's say initial situation, I know what is happening. Initial situation, let's say the density of candle is rho c, density of liquid is rho l. Then what I can write, total weight of candle is 2l length, density multiplied by, let's say A is the area of cross section, so this is the volume multiplied by density, the mass into G, weight. This is balanced by only L length of the L into length into A is the area. This is the volume of displaced liquid multiplied by density of liquid into G, and simplifying it, A gets cancelled, LL, we are getting candle is equal to rho liquid by 2. Okay, and let me consider after some time its X length has burned. Then how much length of the candle is remaining? 2L minus X. And let me calculate how much length inside is required to balance its weight so that it's still staying there. Is it? So let at time t, X length of candle burn. Right? Then let me calculate how much length must be inside. So let calculate the length of candle required inside liquid. So this I can write, total weight of the candle is how much? 2L minus X, this into area is the volume of the candle, multiplied by density of candle into G, this is the weight of candle. That must be balanced by, let's say new length is L, I would say the length which is inside is L into area volume multiplied by density of liquid into G. I hope you are understanding. So this is the buoyancy force, volume of displaced liquid, this is now weight. Solving it, GZ gets cancelled, AA gets cancelled, rho C we are getting it rho L by 2, so this is equal to 2L minus X multiplied by how much? This rho C can be written as rho L by 2, rho L, say rho L. Now L is coming out to be, this implies small l is equal to capital L minus X by 2. So you can see it now here, this top end is coming down by, I'm like this burning by X, but here what is happening, inside length changes by L minus X by 2, so means half of the length decreases here, half of the length will decrease there, so overall you can say the top end of the candle will fall at the rate of half of this 2 centimeter per hour, so it will fall at the rate of 1 centimeter per hour. This is about this problem. Let's see the next problem. So here we are given a solid sphere of density eta. Eta is greater than times lighter than water. So let's say density of water, I am taking its rho liquid. Okay. Then density of solid sphere will be equal to what? Density of solid will be density of liquid divided by eta. This is the condition. Suspended in water tank by a string tied to its base as shown in the figure. If mass of the spring is m, then mass of the sphere, it's actually mass of the sphere is given as m, then tension in the string is how much? So why tension will be there? What is happening? Mg force will be acting, some tension in these all balancing the buoyancy force. Simple thing, right? So we just need to balance buoyancy force is equal to tension plus mg. What will be the buoyancy force? Buoyancy force, if its volume is V, then I can add V rho liquid into G is the buoyancy force. Tension I need, and mg. And I can write m will be equal to what? V into rho sphere into V into rho sphere will be equal to m. Or this rho sphere can be written in terms of rho liquid, so that is equal to rho, all right. So rho liquid from here, rho liquid is equal to what? Eta times rho sphere. Let me substitute it here. This implies V, this is rho liquid, eta rho sphere into G is equal to T plus mg. And what is this actually? This quantity V into rho sphere, this is equal to m. So I can write it's eta mg equal to T plus mg, and this implies T is coming out to be mg, taking it out eta minus 1, and this is the problem, that is the tension in the string. So that is how we can simplify this. I hope you are understanding. This is simple. Upward force, buoyancy force, downward force, weight plus tension. You just need to rearrange, rewrite them, just substituting the value of rho L here and writing it this quantity as m, then rearranging it, we are getting answer. So this is next problem. Okay, let's see a few more cases, applications. So another problem is cylindrical vessel of height 90 centimeters capped filled up to brim. So means this is a cylindrical vessel of height 90 centimeter. It's filled completely full up to brim. Okay, it has 4 holes, 1 2 3 4. 4 holes are made on the side of the tank, which are respectively at a height of 20 centimeter, 30 centimeter, 20 centimeter, 30 centimeter, 45 centimeter and 50 centimeter from the horizontal base PQ. This is PQ base, and the water falling at maximum horizontal distance from the vessel comes out from which hole? So this is simple application of the last topic we discussed, like velocity of efflux and then time to fall and the horizontal range. So we derived the result R is equal to under root H into capital H minus small h. This was the general expression when a hole is made at a height of small h from the top surface, is it? And capital H is the total height of the liquid level, then this is the range, and we derived actually R is max for small h is equal to capital H by 2. So by using this result we can answer directly that for which height, whenever, like wherever, which, if there is any possibility, if out of these 4 holes there is one hole lying at this height, then we can directly say that the range for that hole will be maximum. So what is that H? This is coming out to be 90 divided by 2, that is 45 centimeter. Do we have any hole? So this is total 90 centimeter, is it? And then from the third hole, which is at 45 from the bottom, then I can say it will be also at 45 from the top. So that's why the range of water from the hole 3 will be maximum. That is problem 1. Let's see the next problem here. It's there are 2 identical holes of area of cross section A. So here area of cross section A, and this is also area of cross section A. Liquid is filled in this tank of density rho, and 2 identical holes which are opposite side of the tank containing a liquid of density rho. The difference in height between the 2 holes is given as small h. Tank is resting on smooth horizontal surface. The horizontal force which will have to be applied on the tank to keep it in equilibrium. So it is saying like to keep the equilibrium, the tank is placed on smooth horizontal surface, and it's saying to keep the tank in equilibrium we need to apply some horizontal force. First thing is you should understand why we need to apply, is it, and then how much force we need to apply. So let me explain you that concept. First thing is here what is happening from, let's consider this is a tank and it is filled with some liquid, and here I have made one hole. So liquid is coming out from this hole with some velocity v, and this is height h, then I can say v will be equal to under root 2g h. This will be the velocity with which liquid will be coming out. Now initially the system is at rest. You can see when fluid is coming out it is gaining some momentum. So in 1 second, if area of cross section is A, then in 1 second how much liquid is coming out? Is it liquid flowing out in 1 second? That can be written as density multiplied by area multiplied by, in 1 second, V is the meter per second, so in 1 second it will travel V. So that will be like, this is the amount of mass of fluid coming out in 1 second. With what speed? That is equal to, so change in momentum, delta P can be written as mass into velocity, because when the liquid is inside tank it is having 0 velocity. Once it is coming out it is having v velocity, and in 1 second how much liquid is coming out? M. That is equal to, this is the m liquid coming out in 1 second. So change in momentum per second per second. That can be written as m into v, that is equal to rho a v square, and that is which, what is this? This is the force. So means when the liquid is coming out, the liquid is gaining some momentum. This liquid is gaining momentum, and per second change in momentum is rho a v square. So it's gaining, then by Newton's third law it will apply some force, equal amount of force on the tank, right? Understood? So this liquid coming out, it will apply push back recoil, just like when we fire a bullet, then bullet comes out, is it, gun feels the recoil. Exactly. So here what is happening? Water is coming out, liquid is coming out, it will apply a force. We must understand now by this time that the force is given by rho a v square. Now we can use this result here. Let's calculate force from this opening, force from this opening. Whichever is higher, that will be dominating. We need to apply the net force according to that. So this is your concept. So first thing here, let's say the velocity here is v1 and velocity here is v2. Then force applied by this on tank will be, let's say, f1. By this it will be f2. So f1 force can be written as rho a v1 square, f2 force is rho a v2 square, and v1 is equal to, if I take, let's say this height is L, then v1 can be written as under root 2gl, and v2 is equal to under root 2gl plus h. We can substitute, so definitely v2 is higher, so force f2 will be higher. So net force required is equal to how much? F net will be equal to f2 minus f1. So we need to apply net force, external force, in this direction, because on the tank net force is coming in this direction, backward direction. So we need to keep this in equilibrium, we need to apply a counter force, that F external should be in this way, and that is equal to f2 minus f1. Just substitute the values. Rho a v2 square, v2 is this, so this is 2gl plus h minus rho a v1 square is this 2gl, so it's 2gl. So you can say L gets cancelled, and we are getting with F net is equal to, this is 2 rho a g into h, and this is the answer. This is the amount of force you need to apply to keep this tank in equilibrium. Two things would be clear here, that why we need to apply force here and how much we need to apply force. The force required is, if only one hole is there, then it will apply force in opposite direction. Liquid coming out in this direction, it will apply force in that direction. That is given by rho a v square. Rho is the density of the liquid, a is the area of cross section of the opening, v is the velocity with which liquid is coming out of that hole. Two holes are there, so they will apply both force in this direction. Here the velocity is higher, so this force will be higher. So net force on the tank will be in this direction. To balance it, we need to apply force against that. So this is about next problem. Okay, see few more problem. A cylindrical vessel contain liquid of density rho up to height h. Liquid is closed by piston of mass. So here we have cylindrical vessel, and this contain liquid of density rho. So this is a cylindrical vessel containing liquid of density rho and up to height mentioned as small h. And liquid is closed by piston of mass m. So this liquid is closed here by a piston of mass small m. And area of cross section is, so area of cross section for this is capital A. There is a small hole at the bottom of the vessel. So at the bottom of the vessel there is a small hole. This is a hole through which liquid will come out. And there is the speed with which liquid come out of the vessel is, so it will come out with speed v, and this is what we are asked to find. The difference here is that instead of it's simply open to atmosphere, here we have placed a piston of mass m and area of cross section is A. So now let's look at this point 1 and this is point 2. So then what is the pressure? Pressure at point 1, that I can write P1 will be equal to P naught One is the pressure due to atmosphere, plus this piston will also apply one additional pressure, and that will be equal to mg divided by area. So this will be the pressure P1. Again, we will consider this area is quite large compared to this small hole area. Then we can apply Bernoulli's principle between point 1 and 2. So apply Bernoulli principle between point 1 and 2. So then we can write P1, that is equal to P naught plus mg divided by A, plus half rho V square, that is 0, plus rho g, height is h, and this is equal to pressure at point 2, it's P naught plus half rho V square plus 0, rho g h. So now simplifying it, we are getting P naught getting cancelled out, and this is rho V square by 2 is equal to mg by A plus rho g h. This multiplied by 2 divided by rho, we can just send it this side under root this. So this will be the answer. This is the speed with which liquid will come out from this small hole. So small changes are made in this problem, but still you just need to take care of that what changes are happening because this piston is placed. So similarly, like small variations are coming because questions will not come exactly like only just on one model. Small variations will be there. You just need to take care of those small changes. So like here, this piston is creating just additional pressure. You just need to take care of this amount. Remaining things are just normal basic application of Bernoulli's principle. Let's see to the next problem here. So there are two holes O1 and O2. So this is hole O1 and O2, and in tank of height capital H, the water coming out from hole O1 and O2 strike ground at the same point as shown in the figure. Then the relation between H1, H2 and capital H is. So let's check it. So this is H1 height, and this total height is capital H. So definitely we can write this range. Is it range? So let's say solution. So I can write range from for both the hole must be same. So that means range from range for hole O1, that I can write R1 will equal to under root H1 into capital H minus small h1. Similarly, range for hole O2, so R2 will be under root H2 capital H minus small h2. Now because it's saying both are falling at the same point, means R1 and R2 must be same. R1 must be equal to R2. Just this implies under root H1 capital H minus small h must be equal to H2 capital H minus small h2. Let me erase this part. So simplifying it, squaring both sides and squaring both sides, this implies H1 capital H minus small h1, H2 capital H minus small h2, and this H1 capital H H1 square, H2 capital H H2 square. Just taking it, bringing it this side, H2 square minus H1 square, bringing this term this side and taking H capital H common. So this H2 square minus H1 square, I can write it H2 minus H1, H2 plus H1, H2 minus H1 into H. A square minus B square, A minus B, A plus B. This is simply getting cancelled out and we are getting the relation H2 plus H1 is equal to capital H, and this is our desired result. So this is also simple, easy, like just do what is given in the problem. It's saying range for these two holes is same, just we calculated the range, made it equal and just simplified. That's all, we are getting answer. So this is like different applications, you try more problems based on it, and this is all about your fluid mechanics. I hope you enjoyed, I hope you understood. Let's see, continue with your doubts wherever you are facing problem. Thank you.